Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog. Welcome to Contemporary Science Issues. Today, our guest is Dr. Sean Kelly. Dr. Kelly received his PhD in electrical engineering at MIT in 2003. He's with the Boston VA Medical Center and is a visiting scientist at MIT. His work has focused on the development of new medical technologies and especially on medical implant systems such as neural stimulators. Dr. Kelly is a member of the team that has created the remarkable retinal implant, the Electric Eye, that made Time Magazine's 50 Best Inventions list in 2009. Today he explains how vision works and why it's so difficult to restore lost vision. He'll then describe the device that he and the Boston Retinal Implant Project team have created, a device that represents the leading edge of electrical engineering today. The implant gives us an indication of the bright future of medical technology.
Thank you. I'm very happy to be here. I'm going to be discussing the development of a retinal prosthesis to restore some useful vision to the blind. As part of that, I'm going to talk about how the eye and how the visual system works, some of the research going on in this prosthesis field throughout the world, and then I'll talk a little bit about how the Boston Retinal Implant Project is trying to solve this problem. First of all, what is a visual prosthesis? It's an electronic medical implant that is placed either on the eye or in part of the brain that will restore some useful vision to people who've gone blind for various reasons. For most of these devices, it has to do with degeneration of the retinal cells, the rods and the cones. Let's talk a little bit about how the eye works. In the front of the eye, you see there's the cornea, the iris, the lens. These are the parts of the eye that allow light to come in and focus that light on the retina. The retina is the thin neural tissue on the back of the eye. It's very thin, very delicate, and it contains all the nerves that convert the light coming in to nerve signals that are sent back to the brain. In particular, in the center of the retina, you see an area called the macula, and in the center of that, the fovea. These are the areas where there's the most detailed vision. When you focus on something, your center of vision is right in your fovea, and that's the area where there's the highest density of these photoreceptor cells, the rods and the cones. Then those signals are sent through the optic nerve that you see there back to the brain. Let's look at how the retina itself is put together. Light comes in from the front of the eye toward the back. It passes through a number of layers of nerve cells to the rods and the cones, the photoreceptors that are at the back of the eye. Those cells convert that light into nerve signals. And the nerve signals are passed forward through a few layers of cells, bipolar cells, to the ganglion nerve cells. These ganglion cells are the cells that carry that signal back to the brain. Their axons form the optic nerve, which carries the signal back to the visual portion of the brain. Let's look at how the brain is organized, how the whole visual system is organized in the brain. You see the optic nerve comes out of the back of the eye, it goes to the thalamus, where it goes to the lateral geniculate nucleus, and then goes back to the visual cortex, which is at the back of the brain. We always talk about the right side of our brain controlling our left arm, and that's true for motor and sensory parts of the brain, but what about vision? It's not as simple as the right side of our brain controlling our left eye. It's that the right side of our brain controls the left side of our visual field, and that goes into both eyes. So the things you see on the left side of your body enter both of your eyes, and nerves from both eyes actually get to the right side of your brain, and they cross over in the middle in an area called the optic chiasm. So it separates out the visual field into the left side and the right side. So how do people go blind? There are a number of injuries and other things that will cause blindness, but what we're going to focus on today are some degenerative diseases. They're diseases that kill off the rods and the cones, but leave the rest of the retina mostly intact. One of those is age-related macular degeneration. This is a fairly common disease, and it causes a loss of the photoreceptors, death of these rods and cones near the center of vision in the macula, and it works its way outward kind of slowly and in spots. This tends to strike older people, typically age 60 to 80, and it's more common with increasing age. It may take a while to go blind. Very often people will go through their whole life with this disease and never go completely blind, but some people do. There are millions of these cases in the US and tens of millions worldwide. So another disease that causes a similar loss of these photoreceptors is retinitis pigmentosa. This disease causes these rods and cones to decay from the outside, from the periphery, and working in. You will actually end up with tunnel vision before going completely blind. This disease is genetic, and it strikes people across a wide variety of ages. I say here 15 to 60. There are cases of young school children bumping into their desks because they lose this peripheral vision. This disease tends to progress a little more quickly, often a decade or so to go blind, though there's a lot of variation in both diseases. There are about 100,000 cases of retinitis pigmentosa in the United States and 1.7 million cases worldwide. Let's take a look at what it's like to live with retinitis pigmentosa as the vision starts to close off, as you get this tunnel vision. Here we see a couple of children. As you get the tunnel vision, the loss of the peripheral vision, you end up with a very small visual field, and that can be pretty debilitating, and this often leads to complete blindness. So how would a visual prosthesis restore vision to someone? How would this actually work? What happens is this device electrically stimulates the remaining nerve cells. The rods and the cones of the retina are gone, but the ganglion nerve cells are still there. So if those are electrically stimulated, that information still propagates back to the brain, and patients can see kind of a pixelated, a scoreboard-style image. This is not the same as natural vision, but it's better than being blind, and it's useful for walking around a room or identifying objects. So the Boston Retinal Implant Project is working on what is called a subretinal implant. This would go underneath the retina. Here we see the eye and the retina. These diseases kill off the rods and the cones at the back of the eye. Our electrode array would insert where the rods and the cones were and would electrically stimulate the remaining nerve cells. If instead you put the electrode array on the front, right in front of the ganglion nerve cells on the inside of the eye, that would be called an epiretinal implant. Well, how do you get image information to this electrode to deliver to the nerves? The patients would wear a pair of glasses, maybe something like this. A pair of glasses with a camera. There's a coil for transmitting information. The camera picks up an image, which is then conveyed to some kind of a computer controller system which processes that image. That information is then transmitted to the device wirelessly. So there are coils on the glasses which transmit both the image information and also power from an external battery to the implant. So there's no battery that sits on the eye. That implant then delivers electrical stimulating current to those electrodes, which we saw placed in the subretinal space. And then the patient perceives some kind of a representation of that image, hopefully good enough to navigate or identify objects. There are other places that you could put the electrodes if you're doing a retinal implant, or the implant itself if you go into the brain or things like that. I mentioned epiretinal implants, and on the left you see an epiretinal implant that's being developed by a research group and a company in California. On the right, you see a cortical implant being developed by a group in Montreal. There are actually a wide variety of groups developing different kinds of implants throughout the world. Some are placing electrodes on the optic nerve. Here's our map. Let's look at where in the world this kind of research is being done. Cortical implants are being developed in about 5 different places. I mentioned the Montreal group. There are others. The optic nerve, people are trying to place a cuff electrode around the optic nerve or penetrating electrodes to stimulate the nerve that comes out of the back of the eye before the information gets to the brain. A wide variety of groups are doing research on an epiretinal implant where the electrodes would sit inside the eye. And a number of groups are developing a subretinal implant as well. In particular, the Boston Retinal Implant Project is developing an implant whose electrodes would sit in the subretinal space. Any of these devices present a large number of challenges to researchers. Let's talk about some of those. One, surgical challenges. You need to place this implant on the eye, in the brain, on the optic nerve, wherever it's going to go. The electrodes need to remain in their final location for a long time. They need to be securely fastened, but they need to be safely attached. The electronics, there's going to be an electronics package which delivers stimulating current to these electrodes. That needs to be placed somewhere where it won't cause damage, won't be dislodged. So there are a lot of surgical challenges to implant a device like this. There are fabrication challenges. I mentioned microfabrication here. The electrodes are often made of high-tech materials that are selected so that they can safely deliver the current to the tissue. And these electrodes need to be delicate enough to interface with the tissue without physically damaging it. Also, the device itself needs to be packaged in a way that is completely watertight. We put on a raincoat and we think that we are now waterproof with some kind of a plastic layer. Turns out that plastics will allow water vapor to penetrate right through if you leave them in a water environment for long enough. So our first device that I'll talk about in a few minutes was coated in silicone, which is a type of plastic, and we knew that over years water vapor would penetrate that silicone and condense on the other side. So to make a long-term chronic implant, you need some kind of a watertight package that is just completely impervious to water penetration, typically metal or glass or ceramic. There are also electrical engineering challenges. You need some kind of circuit to deliver the electrical current to these electrodes to the nerves. And also you need to deliver image data from an outside camera wirelessly to the implant and also power if you're not going to implant a battery. There are a wide variety of challenges, and that takes a multidisciplinary team. I split this here into the medical side of the team and the engineering side of the team. Our group in particular in Boston has a number of ophthalmologists, surgeons, retinal physiologists to study stimulating nerves and seeing how nerves react, and also an anatomist to understand what happens in these diseases when the rods and cones die off. What happens to the remaining nerve cells? On the engineering side, we have electrical engineers, microfabrication engineers, there are software engineers, some chemists who deal with the electrode materials and also some of the coatings. There's a mechanical engineer to design the package that I'll present in a little bit, and a technician to do a lot of our testing. Plus we have a lot of other companies that we work with. It's really quite a wide project. The Boston Retinal Implant Project, again, is developing this device to treat macular degeneration and retinitis pigmentosa. And our group has been around for over 20 years. It's a collaboration between Massachusetts Institute of Technology, the Massachusetts Eye and Ear Infirmary, the Department of Veterans Affairs, Cornell University, and a few other universities, and many small companies who are working to develop this. We started out trying to prove that this concept would work. So what we did is selected some blind volunteers and placed electrodes in their epiretinal surface, on the epiretinal surface of their eye, just for a few hours. This was an electrode array that connected to outside circuitry, and we would stimulate for a few hours while the patients were in an operating room. The patients reported seeing some spots and some lines. Nothing terribly complex, though. Imagine you're lying on an operating room table, a steel table on your back. You've just woken up from anesthesia, but you're still under a low level of anesthesia, and in a few hours, over a span of a few hours, people are stimulating your periphery with this unusual type of visual input and asking you. It's a very difficult situation to try to learn to use this odd type of vision. But it did prove the concept. In particular, on the left side of the slide here, you see a representation of our electrode array. In the red box are 4 large electrodes that were receiving currents. They were in close contact with the retina. And on the right side, you see what this patient drew. She had a piece of paper and a pencil on the operating room table, and she drew these 4 cloud-like structures. We're actually going to see a video where she describes what she's seeing to us. The electrical stimulating currents were delivered by this box here. It was a pretty simple battery-powered portable stimulator with lots of safety features, 100 different channels to deliver this stimulating current. I'm going to show you a quick video of what these patients saw. And I apologize, the first video is a little bit dark, but you'll hear what's going on. And what you'll hear is a tone that tells the patient that stimulation is about to occur. And then you'll hear the patient describing what she sees. And she describes these 4 areas like clouds that I just displayed. So let's watch this video and see what the patient sees when we do this kind of stimulation.
There just seems to be areas like clouds. You can see blue through the clouds.
So she describes these 4 clouds, which correspond pretty well to the 4 electrodes, but again, not what you call a very complicated image. I'm going to show you one more quick video. In this case, we stimulate 2 electrodes at the end of a row. The patient describes seeing 2 spots. They describe it as 2 spots of blood, just based on the color of the image. And then we stimulate 5 electrodes in a row, and this patient describes these spots running into each other as though they were a line. We finish with a control experiment where the same tone is given to the patient, but no electrical stimulating current is given.
Okay, you ready, Mary?
Mm-hmm.
Here's the first one. Describe that to us.
2 spots of blood.
2 spots of light. How far apart?
They were pretty close
Okay.
and flashing.
And flashing. We're going to ask you to compare that to the following. You ready?
The 2 spots of blood, but they were running into each other.
Excellent. Okay. 2 spots are running into one another. Okay, you ready?
Mm-hmm.
Here we go.
Okay.
Excuse me?
Nothing.
Excellent. Okay.
So as you can see, there's good correlation with what people are reporting seeing and what we're trying to deliver. But the problem is they just can't develop complex shapes in that amount of time. We proved that the concept works, but we really need a way for patients to learn to use this kind of vision. And the way to do that is to put in a chronic implant for a long time, let the patients really learn how to use it. That's what we decided to do. I mentioned earlier delivering power and data to this implant. I want to talk briefly about how you do this. How do you wirelessly deliver something? Everybody has a cell phone. They know that you can get wireless information from another place. But wireless power is something a little bit different. What we see here are 2 coils, 2 loops of wire. And what happens is when you run an alternating current through one of those loops of wire, it creates a magnetic field which spreads out through space. When another coil is in that magnetic field induces an alternating voltage in the second coil. That's how you can move power across a space wirelessly. And if you modulate that current, if you modulate that field, change it a little bit, you can encode information so you can send image information in much the same way as a radio or a cell phone. our first prosthesis, our first implant, looked kind of like this. It's a little flexible piece of plastic, looks a little bit like the Breathe Right strip you put on your nose. That would wrap around the eye, and you can see the coils that would receive the wireless power and the data. There's a circuit there, a little microchip, like a microchip you would find in your computer, that would receive the incoming image data and deliver electrical currents to the electrodes. The electrodes in this case are between the coils. Right in the middle of the coils, you see a small yellow strip. Those are the electrodes. It's a very small, tight space for the surgeon to operate. But this implant went into some eyes for some trials, and it worked fairly well for a number of months. Also, as I mentioned earlier, this was coated in silicone rubber, which was great for a short time, but is not really viable for a chronic implant that you would put in a person for a decade. So there were some problems we needed to fix. We want what's called a hermetic barrier, a watertight barrier, completely impermeable barrier to protect these circuits and keep them from getting attacked by the water in the body. We wanted larger telemetry coils, these wireless power and data coils that were on the side of the eye. We moved them to the front, made them a little larger. Also, that space to operate between those coils was very small for the surgeon, so we redesigned it to give a little more space. Now you can see the electrode array is in its own area. The coils are up in the front, they're a little bit bigger. What you also see here is a titanium case. This is just like a pacemaker case that you would put in your chest, only much, much smaller. This little titanium case has a bunch of connections from the inside to the outside, which allow the chips inside to deliver current to the electrodes outside, which are then in the subretinal space. On the pictures on the right, you see how we get there. The implant itself sits on the outside of the eye. So to get into the subretinal space, you need to cut through the wall, the sclera of the eye, to get the electrodes in there. And what the surgeons do is they inject a little fluid, lift the retina up out of the way, make this incision, and put those electrodes back into the subretinal space like that. We developed a number of these prototypes, and you can see here there's the chip, the microchip with the little circuit board. That's what decodes the information, delivers the electrical stimulation. And here you see our implant on a model eye, a little plastic eye, and we actually have one of those here. So that's the implant on a little plastic eye, the coils, the case that holds the circuitry, and the electrode array, which inserts through the back. We went through a number of tests of this device in some animal work, and people ask, well, you know how humans would see this because we've done these tests. How do you know what the animal sees? And what we do here is we're just testing whether the implant is still working over time. So what we see here are just a couple of waveforms that show the electrical stimulating current that comes out of the implant. This implant, our first two generations, had a few electrodes, 15, 16 electrodes. It was meant to prove the concept again that we could build this thing, put it in the eye, that it would still work. But really, if you want to restore vision, you want something with hundreds of electrodes. You want something that's going to be able to give patients some kind of image, not the millions of pixels that we have now from our nerves, our rods and cones and nerves in the eye, but something with at least a few hundred. So we're targeting more than 200 electrodes. This is in another hermetic titanium case. It's actually a little bit smaller than the previous one. And the case is being built right now, the coils. Right now we're developing the new chip that's going to go inside of there, the new computer microchip, and also the new electrodes that are going to carry these hundreds of signals into the retina. The next steps in this research are to finish up this 200-channel device, work with the FDA to get approval to start some trials in people, and then also develop this external camera system, this external controller, so that people can then take this device home, walk around with it, and be able to see and learn how to use this new kind of vision to start walking around, identifying objects, things like that. I'd like to thank the research group that made all this possible. It's a large number of people at a large number of institutions. And that's it. Thank you very much.
Sean, we in the general public are maybe accustomed more to hearing about cochlear implants and maybe some other types of implants, but this is rather new. And we know that the vision is extremely complicated. So you've explained very well just how complicated this is and the great advances. But one of the things that struck me here was that materials would be extremely important. You mentioned it needed to be hermetically sealed and so on. Is this something that can only be developed now as materials themselves advance?
That's a great question. First of all, I'd like to compare this project a little bit with the cochlear implant. They're really quite analogous. In the cochlear implant, there are cells that die off that transduce sound into nerve signals, these hair cells in the ear, and an electrode is placed into the ear, into the cochlea, to electrically stimulate remaining nerves. It's very analogous to what we're trying to do here. This device is a little bit different in some ways. It's trying to go onto the eye, so it's a smaller space. The device has to be smaller, and while a cochlear implant may have 16 or 24 electrodes typically, somewhere in that range, if you want to create some kind of vision, you want hundreds of electrodes to really create an image. So that's a challenge. And you're right that the materials that go into this, while many of these are similar materials to devices that have been designed in the past, like pacemakers for the heart, just the density of what's called feed-throughs, the density of connections from inside this case to outside is just so much higher. And it's really been in the last 10 or even 5 years that this technology has moved forward enough to allow us to try to build a retinal implant with this many electrodes, with this many contacts to the nerves.
Yeah, so there's an engineering plus a materials kind of in tandem development there. Then there's another thing for clarification is that with say cochlear implants, things where you're dealing with the brain experiences a great noise in the sense of confusion, not being able to sort the sensory data out in a coherent manner. In restoring sight like this, is that a very big problem? I wasn't sure whether it takes weeks, months, or they get up off the operating table. And
Absolutely. It's a big challenge. And you talk about noise in the brain. If you go completely blind, you don't see black, you see kind of gray and strange things that just don't correlate with what you see outside, but it's not completely black. It's visual noise. You have the same kind of problem with a retinal implant as you have with a cochlear implant, in that it's a completely different signal than your body is used to. And part of what determines the success of a cochlear implant is how available that brain material is to new signals. So if someone goes deaf and is deaf for a very, very long time, what happens is other areas of the brain will start to encroach and use that space. The same is true in a retinal implant. If someone is blind for a very, very long time, other parts of the brain will start to try and use that space. And it's less open, less available for this kind of electrical input. But otherwise, you're right, it will take a long time for people to understand how to use this device, understand how to use this new form of vision.
Right, so it's going to be a lot of experimenting, both on the part of the patient and the teams devising this kind of stuff.
Absolutely.
That was another thing is that I'm impressed with how huge this interdisciplinary effort is. You have all kinds of people, as you mentioned there, all kinds of specialties. Is this the typical picture of the future with these engineering endeavors?
I think so. I think that a lot of these devices are just incredibly complex to build, and this has to interface with the body, and so you need a medical team to understand where best to put the case or how to surgically insert this thing, how it should be made biocompatible. A device as complex as this really does require that interdisciplinary team.
Right. It's a very impressive direction. It really is very exciting to be in this. And so I just have to ask you in closing, how did you ever get into this? I know electrical engineering is kind of like the future. It's in everything, and it's very diverse, a lot of different specialties, but this must be quite rewarding, for one thing. But did you have a medical interest or anything that got you into this?
I did. I decided that I was interested in electrical engineering a long time ago when I was in grade school or something. And I had a brother who was working with patients who had implantable pacemakers, defibrillators, things like that. He was a nurse, so I had exposure to the medical side as well. And that really got me thinking about how to interface these two things, electrical engineering and medicine. And I first found out about the retinal prosthesis project just when I was beginning graduate school. And I instantly realized that that's what I wanted to work on. It's a very exciting and challenging project.
It is that, but it sounds like you are certainly well matched to this field. It's very interesting to talk with you, and thank you so much for doing this program for us.
Well, thank you very much. It was my pleasure.